Hey there, it's your old pal Mr. Cook. Now we're doing page 2 from the supplemental review from Unit 1. Alright, so this says to state the common function, then describe the sequence of transformation. Remember that order is important. So just a reminder that when we do transformations, we need to remember that if we have some function, we got to watch out for where the variable values are and what's happening to the variable values. So let's see here, write it up like this, there we go, and then an A in front and negatives on it. Okay, so these are all the possible transformations that we could have. Each one of them means something. All right, so I'm going to first rearrange this because it's not in the standard form that we're used to. Usually we like the 6, if it's adding on to our function, to be to the right there. So I'm going to just move that 6 over. That's it, just add it over on this side instead, just move it around so I have a negative absolute value of x plus 5. I'll make sure to make those absolute values nice and big so that I know it's not like a 51, and then plus 6 at the very end. There we go. So I can tell exactly what's going on here just by moving that 6 over. Just watch out for that, because just because the 6 is in front does not mean that that's the a value. This is a 6 that's adding on to this function, so it's actually like the k value that tells you if the function is going up or down. Anyways, so we have a plus 5 inside of the function. So if it's inside the function, that affects the x value. And if it's adding, that means it's moving to the left. So one transformation we have is that it's moving to the left by 5. This plus 6 is going to be this k value, which affects the y value in general. And since it's adding 6, it's going to be moving up by 6 units. And then this negative is on the function itself, which means that it's going to be reflecting over the x-axis. So and also a reflection over the x-axis. Okay, and then it also wants us to find the common function. Well, it's an absolute value function, so y is equal to absolute value of x will be our common function. So once again, absolute value is our common function. Just like state the basic function that you have there. This negative out front affects the whole y value, the whole function, so it's going to be a reflection of the x-axis. Since we have a plus 5 inside the function, we're going to be moving left 5 units, and then also since we have plus 6 outside the function, it's going to be moving the whole thing up 6 units. All right, so similarly, we're going to look at this one, x squared. So I mean, that's the common function right there. That's pretty obvious, just because it's a square function. I'm going to rewrite this a different way, just so then you can see like what exactly is going on here. There's no changes on the x values. So this is going to seem kind of weird, but I'm just going to try to get the point across here of what's going on. I'm going to change that x to an x minus 0. And you'll see that, like, you know, this is the standard way that we write up transformations. It's just that, like, when it's x by itself, it's just the arbitrary case that we're adding or subtracting 0, so we're not moving left or right at all. But I just want to like point out that that's what's going on here in case it looked a little weird to you. Then we have this minus 4, which is the k value, so that moves the whole graph up or down. In this case, it's going to be moving it down by 4 units. There's no negatives on the function or the x, so there's no reflection, but there is this 1/2 that's multiplying on our common function, x squared. And that means that it's the a value. And when the a value is greater than 1, you know, like a 5, 6, 7, 8, whatever, the absolute value of the a value is greater than 1, then we have a vertical stretch. In this case, since the a value is between 0 and 1, then that means that we have a vertical compression. I'm just going to write VC for vertical compression, and it's of a factor of 1/2. Okay, so those are our two transformations, vertical compression, and also the graph moves down 4. Moving on, now we do determine the average rate of change for these two intervals with this function. All right, so just a brief rundown of average rate of change. It's just really slope. That's all that it really represents. You know, that the slope is really the average rate of change between 2 points on a linear equation. Average rate of change just finds the slope essentially for any function. So in this case, it's a quadratic. We still handle it the same way. We've got two x values, 0 and 5. That's where I get my x values from here. So that gives us the x part of 2 coordinates. Same thing over here. My two x values are -2 and 2, so I write up 2 coordinates, -2 and 2, and then I got to find the corresponding y values. So for here, I'm going to take the x values and plug them into this function up here. So if I plug in 0, this turns into a 0, this turns into a 0, and I just have 7 left over. If I want to plug in 5, let's use our calculators for that. Why not? So wherever we see an x, we're going to put in parentheses 5. So we're going to do 3 parentheses 5 squared minus 2 parentheses 5 and then plus 7, and it gives us an answer of 72. So 72 is going to be the number that goes there. And then we just need to do slope here. So y2 minus y1 over x2 minus x1. All right, so 72 minus 7 is going to give me 65. 5 minus 0 is 5. 65 over 5 is going to be, oh boy, let's see, 13? Yeah, so 13 is my average rate of change here. All right, moving on to the other one. If I plug in -2, let's do the same thing with -2. So 3 times parentheses -2 minus 2 times parentheses -2 and then plus 7. Oops, I forgot to square, didn't I? Oh man, I got to rewrite that whole thing. Well, actually, on your calculator, you can hit second and then enter, and that'll rewrite the entire thing. So I can just go right over to where I needed to put a square, and I'll put a square there. I think I can put it there. Yeah, there. Oops, I got to insert it. There we go, negative. Okay. So we are all good, and then we hit enter, and we got our value 23 from when we plug in -2. And then I'm going to use that same trick and just get rid of the negatives on the 2's for the other x value. Okay, hit enter and I get 15. All right, so then I do the slope, y2, 23, minus y1, 15, over x2, -2, minus x1, which is 2. 23 minus 15 is going to give me a positive 8. -2 minus 2 is -4. 8 divided by -4 gives me a -2. So -2 is my average rate of change. All right, simple enough. Now we deal with difference quotient. Now, this is a quadratic. This is like on the harder side of the difference quotient problems that we would give you. You know, expect to see a linear equation for the most part here. You know, that should be pretty obvious. I'm sure that, you know, we made several points of emphasis on that. But either way, just remember that this part is a regular old composition. X plus h gets plugged into the input, the x value, and then that's the regular function f of x. So here's how we write it up. So we write this function, 2 blank squared, so 2x squared, minus 3 times blank. And in that blank, we're going to put x plus h. There we go. And then now we're going to subtract away the entire original function, so minus f of x, which is just 2x to the second power minus 3x. There we go. And then the whole thing is over h. All right, so x plus h squared. So I've done that a ton of times when I practice my difference quotient. I know that that's just going to be x squared plus 2xh plus h squared. So that's this part of it, x plus h squared. Now I still got to multiply that by 2, because remember, I'm doing order of operations, so I have to square this first before I multiply everything in. Next, I'm going to distribute the -3 into the x and also the h, so I get a -3x and a -3h. And then I'm also going to distribute the negative into this 2x squared and also this -3x. So the negative of 2x squared is -2x squared. The negative of -3x is a positive 3x all over h. Okay, now I'm going to distribute the 2 in here and see what I get. So 2 times x squared is 2x squared. 2 times 2xh is 4xh. 2 times h squared is 2h squared. And then I have this minus 3x, minus 3h, minus 2x squared, and plus 3x. So the nice thing about this, as always, is that a ton of terms are going to cancel out, like this 2x squared, and this -2x squared, and this 3x, and this -3x. So what we're left with is 3 terms on top, 4xh plus 2h squared minus 3h all over h. Now I get to do the fun task of dividing out the h's here. So 4xh divide out an h, I just get 4x left over. 2h squared divide out an h, so an h goes away and I get plus 2h. And then -3h divided by h, the h gets divided out and I'm just left with -3. There is the answer for my difference quotient right there. And if you need some extra practice with difference quotient, just reference back to some of the earlier videos where I go over, I think, like a couple of difference quotient examples at least. All right, so find the following combinations, then determine the domain and evaluate the combination of the functions when, and evaluate the combination of the functions. So that's all this part where we have to plug in the numbers afterwards. So let's go ahead and take a look at those. So this says f minus g. That is literally just take the f function, f of x, and subtract away the g function, g of x. So the f of x function is x squared minus 16, and then we're going to subtract away the entire function g of x, so 3x minus 12. But here's something you need to remember. Make sure you put parentheses around that second function that you're subtracting, because when you distribute the negative in there, it needs to get onto every single term in there, and that's what the parentheses are good for. So x squared minus 16 minus 3x and then plus 12. Then when we combine like terms, we get our solution, which is going to be x squared minus 3x, and then negative 16 and positive 12 gives me a negative 4. Since this is a quadratic, it doesn't have any of those kooky domain restrictions, so the domain is going to be all real numbers. Remember that our kooky domain restrictions are the rational functions, the radical functions, and then combinations of those two. All right, so now what this notation says is that we take that function that we just put together, and we're going to plug in 2 for x. So if I plug in 2 for x, I get 2 squared, which is 4, minus 3 times 2, which is 6, and then minus 4. 4 minus 4 is 0, so I'm just left with that negative 6 for my answer. All right, next part. So this says I'm going to take the f function and multiply it times the g function. So that's exactly what I'm going to do. I'm going to take the f function, which is x squared minus 16, and I'm going to multiply it times the g function, which is 3x minus 12. All right, looks like I'm getting dangerously close to the other stuff that I'm running. So I'm going to switch over to a pencil so we can, see the difference between, the work that I have here and then the work that I'm going to show over here. So x squared times 3x squared is going to be, of course, my pencil breaks immediately. It has some weak lead. Okay, so here we go. X squared times 3x is going to be 3x to the third power because it's x squared times x, so x to the third. X squared times negative 12 is going to be a negative 12x squared. Negative 16 times 3x is going to be a negative 48x. And negative 16 times negative 12 is going to be a positive, oh geez, let's see. So that's going to be 144 plus 48, so 192. Oh, I'm going to check on my calculator. It's late in the day. I don't trust my multiplication. So let's see, negative 16 times negative 12. Yeah, 192. Okay, so pretty good there. All right. You can't combine any like terms, so this just is your function when you multiply everything out. Now what this notation says is take the function and plug in negative 1, so we're going to plug in negative 1. And since this is a polynomial, it doesn't have any of those restrictions that we're used to. The domain is going to be all real numbers. So if I plug in negative 1, I get, let's see, negative 1 to the third times 3 is negative 3. Negative 1 squared is 1. 1 times negative 12 is negative 12. Negative 1 times negative 48 is a positive 48. And then we have that plus 192. So 192 and 48 is going to be 240. 240 minus 3 is 237. Oh, and then 237 minus 12 is going to be 225. I'm just going to do it on my calculator again. Late in the day, I don't want to make any mistakes. So negative 3, and then minus 12, and then plus 48, and then plus 192. Yeah, 225. Okay, so 225 is our answer there, 225. All right, now let's take a look at this one. So I'm going to move over to my red pen again. This says take the f function and divide out the g function. So I'm just going to put those two on top of each other, x squared minus 16 on the top because that's the f function, and then 3x minus 12 in the bottom. That's my g function. Okay, so first off, I notice that I can factor both of these right now. So x squared minus 16 is a difference of squares expression, so that turns into x plus 4, x minus 4. And then in the bottom part, 3 divides out of both 12 and 3, so I can factor out a 3 and I get x minus 4. Notice that the x minus 4's cancel out, so they're gone, and I'm just left with x plus 4 over 3 for my answer. Now, when we're taking into account the domain, we actually have to reference back to our original function, and since this was a rational function with an x in the denominator, we still have to do the same rules that we talked about earlier. Just take that function, 3x minus 12, and say that it cannot equal 0, and then solve for x. So if we add 12 to both sides, we see that 3x cannot be equal to 12, And if we divide by 3, we know that x cannot be equal to 4. So that's our domain. X cannot be equal to 4. And since we're trying to plug in 4 over here, it's actually a domain restriction. So there's going to be no solution for this one because 4 is not in our domain. That's a tricky one, right? So you got to watch out for stuff like that. Okay, number 13 is all about composite functions. So we're going to look at the composite functions and then also state the domains. And then it looks like this last part here is that we're going to plug in -1. So the composite function is f of g. So I'm going to write that out, f of g of x. So in my class, I've been telling everybody to put parentheses around that circle thing right there, and that tells you what your inside function is going to be. Your input function is that g of x. So we're going to take the f function and use it as a template, the square root of something, and what that something is that we're going to plug in is the whole g of x function, so 2x minus 3. Okay, so we're going to look at the individual parts of this to see what we can do with the -1 and then also solving the entire thing. First off, we know that when we do a square root, that the inside the square root needs to be a positive number or 0. So we're just going to check real quick and see if -1 is going to affect it in any way. So if we plug in -1 times 2 is going to be -2, and unfortunately, when we multiply those numbers together, we get -5 after adding the -3. So the answer for this one is going to be no real solutions for our answers because we can't take the square root of a negative just yet. As for the domain itself, well, what we need to do is take into account this function right over here. So what we do is we take 2x minus 3, and we since it's a radical expression, it has to be greater than or equal to 0. So we solve. And let's see, add 3 to both sides, so 2x has to be greater than or equal to 3. That means that x has to be greater than or equal to 3 over 2. Okay, so there's our domain. X has to be greater than or equal to 3 over 2. And then our function, of course, was the one that we came up with over here, the square root of 2x minus 3. Okay, so we have another composite function, f of g. So the f function is going to be our default expression, so 2 over blank, so 2 over x, and that x value is going to go the entirety of the g function, x squared minus 4. All right, so if we were to take this function and find its domain, this again is just going to be a rational expression, so what we're going to do is take x squared minus 4 and say that it cannot be equal to 0, and then solve it. So x squared cannot be equal to 4, and that means that x cannot be equal to plus or minus 2. Okay, so that means that's our domain restrictions. X cannot be equal to plus or minus 2, and it just so happens that that's one of the numbers that we're trying to plug in over here. So again, we're going to have kind of a weird kind of situation. No real solutions for this one as well. I guess we're not going to have any practice plugging in numbers again. Then the last thing is that composite function, so I'm just going to rewrite it on there, 2 over x squared minus 4. All right, so that's the second page. I hope that it's going pretty easily for you. If it isn't, that's okay. We still got another day to review, so make sure that you ask for help. All right, that's it. Now we're going to move on to the third page.